Okay guys, welcome to this vodcast, the first of a two-part series that will finish off vector functions. This vodcast will be looking at concepts such as distance versus displacement, speed versus change in velocity, change in displacement versus distance, all the same sort of concepts we covered in kinematics, in motion in 1D, will be relating to vector functions, that is motion in 2 and 3 dimensions. So it's quite interesting, and it gets into some interesting calculus that we've seen before. But we're going to start this vodcast with the following, with a series of multiple choice questions that will just recall how things were back in kinematics. We'll just, so have a go at these four. Pause it when you're ready, have a crack at the problem, and then we'll go over the solution. Okay, so I'd imagine you've had a go at this problem by now. It's talking about a particle moving with constant acceleration, initial speed u, final speed v. We need to work out its speed at the midway point. Okay, so a couple of ways we might think about it. So the first thing is constant acceleration formulas versus velocity time graph. So sometimes one is more helpful than the other. Now, velocity time graph is, of course, immediately linking time into the equation. Time isn't given to us in the given information. We can do it with a velocity time graph, but with a lot more work. So this would be a situation where our formulas for constant acceleration would be helpful indeed. So, of course, what links final velocity, initial velocity, and distance covered, v squared equals u squared plus 2as in a situation of constant acceleration. What this means is we can get an expression for the total distance traveled over the journey from A to B, and at the halfway point, it would be represented by that particular expression. Now, you don't see acceleration in the final expression for the particle speed at the midway point, but if we return to v squared equals u squared plus 2as and replace s with the given expression you see before you, you'll notice that the a's will cancel. And by doing that, so the speed at the midway point, vm squared is u squared plus 2a times that expression. Crossing out the a's leads to this expression, collecting your u's, and then taking the square root makes e the answer. Of course, we drop the negative because it's a constant acceleration that we're in this particular situation we're holding to be positive. So there we go. That's how you do that particular question. Okay, here's the next problem in our series of 4 problem starters. It's a really nice question. It's a little different. It's an acceleration versus time graph in this particular instance for a journey over 60 seconds. Take note of all the information and see if you can come up with the correct response. I'll go over the solution shortly. Okay, you're back and you're interested in how a solution is obtained for this particular question. Acceleration versus time graph. So obviously area under the curve this time represents velocity rather than displacement. So change in velocity rather. So firstly, let's note it starts from rest. Okay, so initially the initial velocity is equal to 0, and as time is growing, it's experiencing acceleration in the positive direction, albeit uniformly decreasing. So a couple of ways we could go about it. We could use our calculus. We could get a rule for that straight line. C is 3, gradient is minus 1/10. We can integrate from 0 to 30. And of course, plus 0 is just emphasizing the fact that it's starting from rest, or simply half base times height, and of course, leading to the answer that is B. So it reaches a speed of 45 seconds, 45 meters per second after 30 seconds. And then because it experiences 0 acceleration, it just maintains that speed for the next 30 seconds. So nice little problem, nice little problem. Now, I've got a question for you. Okay, what would be the particle speed if that uniform change in acceleration that you see occurring over the first 30 seconds continued for another 30 seconds? Just have a think about it. So I'll pause it again, have a think, and then see if you can come up with the answer. Okay, so as you can see, that particle starts from rest, experiences a positive acceleration that's gradually slowing, but starts off at 3 meters per second and progresses on to zero uniformly after 30 seconds, but it's causing its speed to increase. So after 30 seconds, hits that top speed of 45 meters per second, which it maintains for the next 30 seconds. But if it was continuing that slope in my acceleration versus time graph, if that slope continued, after 30 seconds, once it's hit the top speed, it'll start to experience an acceleration in the opposite direction, causing it to slow. So of course, it's experiencing a growing acceleration in the opposite direction. And if we continue that graph onwards, for the area above the curve to be equal to the, above the t-axis to be equal to the area below the t-axis, after another 30 seconds that would occur. And after the first 30 seconds hits that top speed of 45 seconds, and another 30 seconds continuing on with that uniform rate of change of acceleration, it would return to zero. So the answer to that question would be, if it continued along in that manner, it would return to rest after 60 seconds. Okay, here's another 2 questions, in fact, and I've just tagged on question 2. So what we've got is the acceleration of an object inversely proportional to its velocity at any time t, some information about its velocity at a particular acceleration, and we need to, and some initial information there, and we need to come up with the correct expression relating velocity and time. I'll let you have a go at this problem, and then I'll pause it in a moment, and then we can go over the solution together. Okay, so the first thing you would do is set up your expression relating acceleration and velocity being inversely proportional. There's your K, your constant of proportionality, and that second sentence there is all about giving you values that you can evaluate K with, the constant of proportionality. So obviously K is equal to 3. Okay, leading to the expression between acceleration and velocity. All right, what else do we know? We know that the initial velocity, in other words, the velocity when time is equal to 0, is equal to -2, 2 to the left. All right, so we go through the usual routine. We need to express acceleration as what? Ultimately, what do we want? We want a relationship between velocity and time. Our initial conditions are between velocity and time. Therefore, we express acceleration as dv dt. Okay, so it's that routine. You've got to pick out the right expression for acceleration for the given situation. What do? We invert it, we anti-derive t with respect to v, and hopefully you get the following expression. T is equal to v squared on 6 minus, v squared minus 4 on 6, so the constant of anti-diff was -2/3, that we just make it into the one expression. Multiplying across by 6, adding 4, taking the square root, plus or minus, and then we need to consider the right form. So multiplying across by 6, adding 4, obviously it's going to be A or B. Which is the correct one? Well, it'll be B because of the initial condition being 2 to the left. Okay, so always remember, that's how you determine your plus or minus situation. Okay, have a look at question 2. It's the same relationship between acceleration and velocity. However, this time we're told information about where it's starting at the origin, and we need to find a relationship this time between velocity and displacement between v and x. What form of acceleration do we use in this instance? I'll pause it and let you have a go. Okay, so you're back now, you're ready to look over the solution. Okay, hopefully most of you realize, because the expression for acceleration is in terms of v dv dx is the way to go. Dividing through by v, flipping it over, anti-deriving it, and we're told v initially has a velocity of 2 to the left. It starts at the origin, so we're going to replace x with 0 and v with -2. Okay, moving on, leading to a c value of 8 on 9, and then we rearrange to make velocity the expression. And there is no plus or minus in this instance, which is nice because it's the cube root. So that's quite a handy situation, less to think about. Okay, good. We're ready for our final question. All right, folks, welcome to the final of our preliminary problems, reviewing previous work. Okay, what have we got here? We've got a position vector function changing with respect to time in 2 dimensions only, i's and j's. T represents time. Not sure why t can't be 0, but t must be greater than 0. So at some particular time, let's call it p, the particle crosses the x-axis. Okay, what we need to do is find the acute angle. So if we think of the tangent to the path as marking a straight line crossing through the x-axis, one angle will be acute, one will be obtuse. We need to pick out the acute angle that the path is crossing through the x-axis. All right, I'll let you have a go. I'll pause it for now, and when you come back, we'll go over the solution. All right, let's go over this. So the first part to fact to establish is what is the time it takes for this path to cross through the x-axis. Now, some of you may have got a Cartesian equation and they're replaced y with 0 and solve for x, but there is a much easier way, of course. It's when the j component is 0. Okay, so remember, it's a position vector function changing with respect to time, pointing to if we collect all the endpoints, we've got our Cartesian equation, but it points to its position in 2-dimensional space. And obviously, when there is a 0j component, it's at the point where it's crossing the x-axis. So the easiest way is to just let 4 minus t, the coefficient of j, equals 0 and solve for it, and we get t is equal to 4. So hopefully some of you went down that track. All right, now we know the time at which it takes for it to cross the x-axis. We now need to work out the angle at which it's crossing the x-axis. So hopefully there's a couple of ways we can go about this. We know the velocity vector function drives direction, so that's one approach. Another approach is in fact to get an expression for dy dx in terms of t using the chain rule. So this is just one approach you could take. Let y as a function of t be the j component, 4 minus t. Let x as a function of t be the function assigned to the I component. So we derive that and we reciprocate it. So the derivative of t to the half plus 1 is half t to the minus the half. Okay. And the derivative of 4 minus t is just minus 1. So there it is. So there's the two components multiplied together, divided by, it flips over, and we've got that expression for, it's a generalized expression. It's kind of neat. We can determine the gradient of our path for a particular time t using the chain rule in that manner. So then we replace t with 4, and we have to work out our, we've therefore worked out the gradient when t is equal to 4, when it's crossing the x-axis, and then we of course appeal to m equals tan theta, inverse tan applied to minus 4, and we take, if that's obviously going to give us an obtuse angle, we just take the acute equivalent. So we could have just gone inverse tan 4. Here's another way. Okay, we could have used appeal to the velocity vector function as said before. So r dot of t is equal to that. And so the gradient will be equal to rise over run. So our j component over our I component. So we substitute t equals 4 into the rule. Our j component has a value of minus 1. Our I component has a value of 1/4, rise over run, leading to the same endpoint. The angle at which is crossing the x-axis from the positive side will be the inverse tan of minus 4 rather, but of course we just need to take the supplement of that, and it turns out to be 76 degrees. Wonder how you went with those 4 problems. I think they each had a lot of merit in terms of tapping into your level of understanding. Hopefully you've gained something from those. Now let's move into today's lesson. Okay, so in this podcast we'll be looking at the idea or the concepts of velocity and acceleration, both instantaneous and average, as a particle is moving along a path in 2D space in particular, and maybe on occasion in 3D space. Okay, so it's the final installment, and from here it'll lead into a second podcast that will look at a particular application of these skills, that is in projectile motion. So it brings up a few interesting ideas in its own right. Okay guys, we're already familiar with these concepts. So our velocity vector function is derived from our position vector function. Okay, we classically assign x and y to our function assigned to i's and j's. So deriving those expressions separately gives rise to our velocity vector function, and it's always the velocity vector function that drives direction. So just don't forget that. That's one of the key concepts in this unit. Velocity vector function drives direction. Acceleration vector function is obviously a derivative of the velocity vector function or a double derivative of the position vector function. There you have it. Uses of dots or dashes are interchangeable. Now speed, we haven't talked about that. We've got a couple of versions of speed, instantaneous and average. Instantaneous is quite easy. We take our velocity vector function and think of its magnitude. So it too is a function of time. So what do I mean by that? Okay, firstly, we work with that when asked to find, that's our go-to whenever we're asked to find the min or max speed, which is a common question. And you can use calculus, or if it's a function in terms of sines and causes, sometimes it can be just deduced from the form of the expressions. Understanding sine and cos both have a min and max of -1 and 1 respectively. But what is what does that expression look like? That would be it. So we take our function of time assigned to I, our function of time assigned to j, we square them, we sum them, square root. It's just that's by virtue of the magnitude is what we're after. So remember those concepts. We'll be building on them going forward. Okay, you'll be required to calculate distance between 2 points along a path. There's two types of questions you'll encounter. One is the direct line distance between those 2 points on the path, and this was related in developing our understanding of r dot t via first principles calculus. So it's obviously its position vector function at the end of the time interval minus its position vector function at the start of that time interval, and we take its magnitude. So that's obviously directly related to the length of the vector from point A at t0 to point B at t1. So it has that direct connection to our understanding of vector and vector length, okay, as the shortest or straight line distance between 2 points on the curve. Now, a more sophisticated question of distance comes from our arc length formula, way back in 8E. In fact, this is where the parametric version comes into play. So you recall this version of arc length, I'm sure. So obviously, when it hits the time at t equals A to the time at t equals B, we just apply this formula. So we're integrating from A to B. It's our x dot expression squared plus our y dot expression squared, the sum and the square root, and we integrate that way. So that gives us our distance along the curve, certainly not the straightest line distance, but it is the distance it travels from the point on the curve at t equals A to a point on the curve at t equals B. Okay guys, take note of these two very important formulas, and I hope you understand their derivation. Okay, one is for average velocity over a time interval, and the other one is average speed over a time interval. Drawing on your understanding from kinematics, motion in one direction, understand what average velocity is all about. It's change in displacement over the time interval. Okay, now of course, if we're not traveling in one dimensions, where change in displacement only differs by a positive or minus, what we're dealing with is position vector functions ij or ijk expressions if it's in 3 dimensions. So that's what we've got here. Let's take note of that. So this top, the numerator part of the expression, is your change in position, change in displacement, and we're expecting it to be a vector expression in terms of i's and j's, okay? So it's meant to should have an I and a j component, okay? So you're expecting that over the time interval. So average velocity should be expressed as a change in position over the time interval. Okay, now what do we know about average speed? Okay, here's our average speed. Okay, average speed is distance traveled over the time interval over the change in time. Aha. Okay, this expression here relates to the distance traveled along a path from T1 to T2, as we've already seen, divided by time is that 1 divided by T2 minus T1 expression. So they make sense, but understand when to use them and how to use them. Okay, hopefully they don't cause too much grief for you. All right, here is a cracker of a problem for you guys. It's in fact the only problem we're going to look at to round out the unit. I think if you can answer A to F, you've actually got it nailed. You can move on to 12D with confidence. Okay, it's given a position vector function, a particle moving. It's obviously got some sort of periodic path in which it'll be traveling on. What we need to do is find a Cartesian expression for the path of the particle. How far along the path does it travel over a particular time interval? The shortest distance between those 2 points on the path it makes. Then we need to work out its average velocity, average speed, and the instantaneous speed at t equals pi on 3. Okay, so it's bringing in to bear all the concepts we raised in the last 2 slides. I think most of you, just by referring back to those slides, should be quite okay with answering these problems. But I'll be presenting the solution shortly and pause it where it suits you. Okay, enjoy. Okay, guys, that's the start of our rule creation. We've got x is sine t, y is half sine 2t, and hopefully most of you would see the need to apply the double angle rule for sine in order to get a single expression of y in terms of x. So we can replace cos t with, so sine squared t plus cos squared t is equal to 1, but by the Pythagorean identity, and we can use that to replace cos t as the square root of 1 minus sine squared t. Yes, but not quite, because we can do that whenever cos t is positive. Okay, in other words, when t transitions from 0 to pi and 2, that's hunky-dory. But when t goes from pi and 2 to pi, cos t is negative. And when t goes from pi to 3 pi and 2, it remains negative. So any t value that takes us into the second or third quadrant will produce a negative cos value. So in fact, really the full expression of this relationship between y and x could be given as follows. Y is plus or minus x times the square root of 1 minus x squared, accounting for the fact that t is going from 0 onto positive infinity, covering first, second, third, fourth, and repeated cycles. Okay, so I'm sure some of you, quite a few of you, missed that particular detail. Okay, so just what would a function like that look like? Well, there it is. So the red version is the positive and the blue version is its reflection in the x, so the negative version. So quite interesting. So let me just grab a pen let's think about this for a moment. So let's just grab black, say. So as t at t equals 0, it's starting there at the origin. Okay, the I component, the j component is both 0. It's transitioning along that path in that direction. As t hits pi on 2, it hits the point 1, 0. Okay, and then as t is growing from pi on 2, sine double that means it becomes negative. Okay, so sine pi, and so the x component remains positive, and the y component, as driven by that j function, becomes negative. So then it travels back towards the origin and returns to the origin at t equals pi. It continues as t equals pi to 3 pi and 2. Pi to 3 pi and 2 both, or now we're doubling it, so double pi is 2 pi, double 3 pi and 2 is 3 pi. This time our x component is negative and our y component is positive, and it hits that point at t equals 3 pi and 2, and then travels back along this lovely looking bow tie of a function is t equals 3 pi and 2 back to 0 at t equals pi, 2 pi, and then it repeats that indefinitely. So let me just get a rubber and remove all of that. So that's just some interesting ways to understand what's actually happening here with the plus or the minus. Okay, let's move on. Okay, I think I can let me just work out what to do with my pen here. Just bear with me a moment. Okay, I'll just click on that. Okay, here we go. Okay, so, all right, so we need to work out the distance it travels from the origin to that point along the curve. In other words, so I'll just grab my pen now, I know what I'm doing here. So it's this distance here I need to calculate until it hits the point when t is equal to pi on 3. So that's the distance I need to calculate, and of course I can do that via my calculus rule. So what do I need to do? I need to take my x expression and differentiate it, my y expression and differentiate it, and then we whack it into that rule for distance. So our distance rule is the integral from 0 to pi on 3. Both of those rules squared, no need to mess around with algebra, whack it straight into your calculator and you get that approximate value. So that approximate distance is 1.061. Okay, then we have to work out the shortest distance from t equals 0 to 3 to pi on 3. And of course it would be given by that straight line. So clearly a straight line function. We can come up with the vector essentially that describes that change in position. How do we do that? So it's position at pi on 3 minus position at 0, and of course its position at 0 is just the origin. So effectively that's the position vector pointing to the point on the path at t equals pi on 3 given by that rule. And the actual distance, the shortest distance, is therefore the magnitude of that position vector. And of course you get root 15 on 4, approximately 0.968. So you can see less than the distance traveled around the curve to that point. Okay, so from there we need to work out our average velocity from t equals 0 to t equals pi on 3. Remember, it's our change in our position over the change in time, so divided by pi on 3. And when we do that calculation, of course, it's position at time pi on 3 minus its initial position, which is the origin, and we get that final expression. It looks strange. There are no units, distance units per time units here, but that's the answer. It should be as a vector in 2 dimensions, as an ij vector. That's appropriate because velocity is, after all, it has distance and magnitude, and that's inbuilt into that as the final answer. Now, if it was the instantaneous speed at t equals pi on 3, that would be a different question, but it's not. It's the average speed from t equals 0 to t equals pi on 3. So what do? We've already worked out the distance, correct to a number of decimal points, and we just simply divide it by the time interval, which is pi on 3 minus 0, or pi on 3, and we've got that as the average speed. Find the speed at t equals pi on 3. Of course, that's just the instantaneous speed. So we take our r dot function, we substitute pi on 3 into it, and we take the magnitude of that particular velocity, instantaneous velocity at time pi on 3. So the magnitude of that is, of course, 1/2 times root 2, or root 2 on 2. There we go. Hopefully you guys are finding this okay. All right, here's just a little bit more practice, in fact. So 3-dimensional travel. We need to work out its velocity at a particular time t, its speed at a time t, and then from there work out the maximum speed and the minimum speed. So see how you go. All right, so I presume you're back to go over the solution. Velocity is, of course, just differentiate each of those component parts once. So r dot of t looks like that, and our speed is taking the magnitude. So 4 cos 2t all squared minus 2 sine 2t all squared plus 2 squared leads to that final expression. Now, as it stands, it's enough. In fact, you can see what we're doing there. You know what? I think I'll jump in there and explain what's going on there in case you can't see it. Of course, that's here. Let me just grab that component over here. That's nothing other than 12 cos squared 2t plus 4 cos squared 2t plus 4 sine squared 2t. This here is just 4 via the Pythagorean identity. So that 4 gets added to the other constant under the square root sign to make plus 8 that you see below. So hopefully that is clear enough for you. Let me just grab my eraser and remove all of that. So let's get rid of that. All right, so hopefully it's clear where that's coming from. And from there, without doing any kind of fancy pants calculus, we can clearly go straight back into appreciating, because the lowest value it can take is -1. When I square it becomes positive 1. The highest value it takes is 1. When I square it is 1. And of course, so the minimum of a cos squared function will be equal to 0. So straight away, I should be able to ascertain the maximum and the minimum speeds as 12 plus 8 square root. And the minimum speed is 0 plus 8 square root of 8. And we can work out the times at which they occur as well. Okay guys, here is the final problem of the session. I'm actually not going to do it for you, but I will reveal the critical steps. It's a 4-step path towards a solution. So have a good read of it. It's an excellent problem. Here are 2 position vector functions for 2 particles A and B. Obviously time starts at 0 and progresses in the positive direction. We need to prove that these particles do collide, and when they collide, they're traveling at the same speed, but they are traveling at right angles to each other. I want you to have a go at this problem. I'm going to pause it soon, and I'll start to reveal the steps involved in being able to answer this question. It's really a very good problem. Okay, so have a go and return, and I'll give you the steps as hints. Okay, you've returned for the hints. So the first thing is obviously in this proof is finding the time when they do collide. Obviously, collision is different to path crossing. It's the easier of the 2 options. We set our I functions equal to each other. We set our J functions equal to each other. We solve for T. We look for that common time T that marks a solution to both of those 2 equations. So maybe I'll just quickly, while I'm here. So essentially, here in terms of our I's, we set out T cubed minus 9T plus 8. We set that equal to 2 minus T squared. We get a solution. And then our other one, T squared, is equal to 3t minus 2. Obviously, t squared minus 3t plus 2 equals 0. So we've got t equals 1 and t equals 2, we see which of those two solutions is the solution to the first equation. We find out the time it takes for them to collide, for a collision to occur. Okay, what's the next step, you ask? Okay, let me just get back into the... Okay, the next step, let me just get rid of that. Hang on a minute. Okay, the next step is to work out their respective velocity vector functions, sub in that time s at which they're colliding into both, and show that the magnitudes of each are equal. Okay, that's showing that they're actually, when they collide, they're traveling at the same speed. So that's what steps 1, 2, and 3 are doing. Okay, and finally, we need to prove that they collide at right angles. What do we do to show that? Okay, so hopefully most of you are onto the fact we're in the field of vectors. What's the easiest way to prove that two vectors are at right angles to one another? And that would be, of course, the dot product. So, so the last thing is, once we've got that time s, which looks like it's t equals 1 or t equals 2, we sub it into our velocity vector, our respective velocity vector functions for particle A and B, show that their dot product is equal to 0, and voila, you've answered the question in full. So hopefully you've had some success with that. Stay tuned for podcast 2.